Imagine you want to teach a machine to recognize a cat. You could show it thousands of pictures and tell it which ones are cats. But what if you don't have labels? What if you have only a few labeled examples and millions of unlabeled ones? Or what if there isn't a correct answer at all and the machine has to discover patterns by itself? And what if the machine learns by taking actions, receiving rewards or penalties, and improving over time? These are fundamentally different ways of learning. In this video, we will understand the major types of machine learning, how each one works, when we use them, and most importantly, how to decide which learning approach fits a real world problem. In first episode, we established what machine learning is. In second episode, we went deeper and understood the learning mechanism. Data goes into a model, the model makes predictions, we calculate the error, and the model adjusts its parameters to improve. Now we need to answer an important question. How exactly do we provide the learning signal to the model? That's where the different types of machine learning comes in. Before we continue, a quick note. You may be wondering about the difference between artificial intelligence, machine learning, deep learning, and generative AI. I have already covered that comparison in detail in my AI Fundamentals for Developers series. I'll put the link to that video in description. So in this machine learning engineer series, I'm not going to repeat that explanation. Instead, we are going deeper into machine learning itself, starting with the different ways a machine can learn. The easiest way to understand the types of machine learning is to ask one question. What information does the model receive during learning? Does it receive examples together with the correct answers? Does it receive only raw data and have to find patterns itself? Does it receive a mixture of labeled and unlabeled data? Or does it interact with an environment and learn from rewards and penalties? Depending on the answer, we get different learning paradigms. We will cover 5 important learning paradigms. The first is supervised learning, then unsupervised learning, then semi-supervised learning, then self-supervised learning, and finally reinforcement learning. Supervised and unsupervised learning are the traditional foundations. Semi-supervised and self-supervised learning become particularly important when labeled data is expensive but large amount of raw data are available. And reinforcement learning is fundamentally different because the model learns through interaction and feedback. Let's start with the most straightforward type, supervised learning. The word supervised gives us an important clue. The model is learning under supervision because we provide examples where the correct answer is already known. For example, suppose we are building a house price prediction model. We might give the model house area, number of bedrooms, location, age of the property, and the corresponding actual house price. The input is the information about the house, the target is the known price. The model learns the relationship between the inputs and the target. The key concept here is the label. A labeled dataset contains both the input and the expected answer. For an email classification problem, the email is the input and spam or not spam is the label. For image classification, the image is the input and cat or dog could be the label. For house price prediction, the features are the input and the actual price is the target. The model uses these examples to learn a mapping from inputs to output. Supervised learning can broadly be divided into two very important problem types, regression and classification. Regression is used when the output is a numerical value. For example, house price, temperature, sales revenue, stock demand, or delivery time. Classification is used when the output belongs to a category. For example, spam or not spam, fraud or legitimate, cat or dog, approved or rejected. Let's make regression concrete. Suppose our model receives 1500 square feet, 3 bedrooms, a particular location, and several other features. The model predicts 1.2 crore rupees. The output is a continuous numerical value. That's regression. We will later spend an entire section learning algorithms such as linear regression, decision tree regression, random forest regression, and other techniques. Now consider an email. The model analyzes the email's features or text and predicts spam. This is classification because we are choosing between categories, and classification doesn't necessarily mean only two categories. Binary classification has two classes, for example, spam or not spam, but multi-class classification can have many classes. For example, an image classifier might predict cat, dog, horse, bird, or a car. So classification is about predicting a discrete category. Now connect this to our previous episode. In supervised learning, we have the correct answer. The model makes a prediction. We compare that prediction against the actual target. The difference is captured by a loss function. Then optimization techniques such as gradient descent help adjust the model parameters. This process repeats over many training examples. So supervised learning is essentially learning from examples where the correct answer is available. Supervised learning is a great choice when historical examples contain the answer you are trying to predict. For example, if you have thousands of previous transactions labeled as fraud or legitimate, you can train a fraud classifier. If you have historical house data containing actual selling prices, you can train a price prediction model. The biggest challenge is usually obtaining high quality labels. And labeling data can be expensive, slow, and sometimes requires human experts. Now let's remove the labels. Suppose I give you a million customer records. I don't tell you which customers belong to which group. I simply ask, can you find meaningful groups or patterns in this data? That's where unsupervised learning comes in. The model isn't given a correct answer for each example. Instead, it tries to discover structure in the data. Imagine an online shopping company has 1 million customers. We might know things like how frequently they purchase, how much they spend, what categories they browse, and how recently they purchased. But nobody has manually labeled these customers as budget shoppers, premium shoppers, frequent shoppers, and so on. An unsupervised algorithm can discover groups of customers with similar behavior. This is called customer segmentation. One of the most important unsupervised learning technique is clustering. The idea is simple. Put similar data points closer together into groups called clusters. For example, customers with similar purchasing behavior may end up in one cluster. Customers with different behavior may end up in another. A famous clustering algorithm is k-means. We will study k-means in much more detail later when we reach unsupervised learning algorithms. Clustering isn't the only thing we can do with unsupervised learning. We can also use it for dimensionality reduction. For example, we might have hundreds of features and want to represent the data using fewer dimensions while preserving important information. We can also use unsupervised techniques for anomaly detection. For example, if most transactions look similar but one transaction looks extremely unusual, that may indicate potential fraud. So, unsupervised learning is primarily about discovering structure when explicit labels aren't available. Supervised learning asks, given these inputs, what should be the answer? Unsupervised learning asks, what structure or patterns exist inside this data? Supervised learning has a target, and unsupervised learning generally doesn't. And this difference determines the algorithms, training process, and evaluation methods we will use. Now, let's consider a very common real world situation. You have 100,000 images, but only 1,000 have been labeled by humans. The remaining 99,000 are unlabeled. Throwing away those 99,000 images would be wasteful, but training a fully supervised model using only 1,000 examples may not be enough. Semi-supervised learning tries to use both sources of information, a small amount of labeled data and a large amount of unlabeled data. Why is this useful? Because labels are often expensive. Imagine medical images. A human expert may need to examine each image and determine whether a particular disease is present. That takes time and expertise. But collecting thousands or millions of unlabeled images may be relatively easy. Semi supervised learning allows us to take advantage of both. Now we reach one of the most important concepts in modern machine learning: self-supervised learning. At first, this sounds confusing. If there are no human labels, how can the model be supervised? The answer is the data itself is used to create the learning signal. We automatically construct a task from the raw data. Consider a sentence: the cat sat on the blank. We can hide one word and ask the model to predict it. The original data set didn't need a human to manually create a label saying mat. We generated the learning task automatically from the data. The original word becomes the target. The surrounding words become the input. The model learns by trying to predict the hidden information. This is incredibly powerful because the world contains enormous amounts of labeled and unlabeled data. Text on the internet, images, audio, video, code. We can't manually label everything. Self supervised learning allows models to learn useful representations from huge amounts of raw data. After that initial learning, the model can often be adapted or fine tuned for specific downstream tasks. This idea is fundamental to many modern AI systems. These two concepts, semi supervised versus self supervised, are easy to confuse. Semi supervised learning explicitly uses some labeled data together with unlabeled data. Self supervised learning creates the training signal from the data itself. So, the key distinction is semi supervised learning uses existing human provided labels plus unlabeled data. Self-supervised learning generates the target automatically from the raw data. Reinforcement learning. Here the model doesn't simply receive a data set containing inputs and correct answers. Instead, an agent interacts with an environment. It takes an action. The environment responds. The agent receives a reward or a penalty. And over time, it learns which actions lead to better outcomes. Imagine teaching an AI to play a game. The agent sees the current state of the game. It can choose an action. Maybe it moves left and loses. That's negative feedback. Then it tries another strategy and moves right, earning a reward. Over thousands or millions of interactions, the agent learns which actions tend to produce better long term outcomes. This is the basic intuition behind reinforcement learning. There is another important difference. In many supervised learning problems, we are primarily concerned with predicting the correct output for an input. Reinforcement learning is about making a sequence of decisions. Today's action can influence tomorrow's situation. For example, in a game, taking a small reward now may put you in a terrible position later. So the agent needs to learn not just immediate rewards, but long term consequences. Another fundamental reinforcement learning concept is the exploration versus exploitation problem. Exploration means trying actions we don't know much about. Maybe they could produce a better result. Exploitation means using an action that we already know works well. If an agent only exploits, it may never discover a better strategy. If it explores too much, it may waste time taking bad actions. A good reinforcement learning system needs to balance these two. Let's bring everything together. Supervised learning learns from known answers. Unsupervised learning discovers hidden structure. Semi-supervised learning combines a small amount of labeled data with a large amount of unlabeled data. Self-supervised learning creates its own learning signal from raw data, and reinforcement learning learns through interaction, rewards, and penalties. Here is an important engineering insight. The same business domain can involve multiple types of machine learning. Suppose we are working with customer data. With supervised learning, we could predict whether a customer will leave. With unsupervised learning, we could discover customer segments. With semi-supervised learning, we could use a small number of labeled customers together with a much larger unlabeled dataset. And self-supervised techniques could learn useful representation from large amounts of raw customer behavior. So the type of learning isn't determined simply by the industry. It's determined by the problem, available data, and the learning signal. When you are working on a real ML project, don't start by asking which algorithms should I use. First ask, do I have labeled data? What exactly I'm trying to achieve, and how does the model receive feedback? If I have labeled examples and want to predict a target, supervised learning may be appropriate. If I have no labels and want to discover structure, unsupervised learning may be appropriate. If I have limited labels and lots of unlabeled data, semi-supervised methods may help. If I can automatically generate learning tasks from raw data, self-supervised learning becomes interesting. And if the problem involves sequential decisions and rewards, reinforcement learning may be appropriate. There is one distinction I want you to remember as an aspiring machine learning engineer. A learning paradigm is not the same thing as an algorithm. For example, supervised learning is a learning paradigm. Under supervised learning, we can use many different algorithms: linear regression, logistic regression, decision trees, random forest, support, vector machines, neural networks. Similarly, unsupervised learning has algorithms such as k-means and other clustering and dimensionality reduction techniques. So don't confuse supervised learning with a specific algorithm. This is the mental model I want you to develop. First, understand the problem, then decide what learning paradigm fits, then select an appropriate algorithm. That algorithm gives you a model structure. You train the model using your data, and finally, you evaluate whether it actually works. As we progress through this series, we will go deeper into every one of these stages. A common beginner mistake is asking which machine learning algorithm is the best. There is no universally best algorithm. A better engineer asks, what problem am I solving? What data do I have? Do I have labels? How much data do I have? What is the target? Only after answering these questions should we start selecting algorithm. Let's quickly connect these concepts to real world applications. Supervised learning can be used for fraud detection and price prediction. Unsupervised learning can be used for customer segmentation and discovering unusual behavior. Self-supervised learning is extremely useful when we have huge amounts of raw text, images, audio, or other data and want models to learn useful representations. Reinforcement learning is useful for problems involving sequential decisions such as games, robotics, and certain control problems. The real world can also combine multiple approaches. So let's recap. Supervised learning learns from labeled examples. Unsupervised learning discovers patterns without explicit labels. Semi-supervised learning combines labeled and unlabeled data. Self-supervised learning generates a learning signal from the data itself. And reinforcement learning learns through actions, feedback, rewards, and penalties. If you remember only one thing from this video, remember these questions. What data do I have? Do I have labels? What exactly am I trying to predict or discover? And how does the model receive its learning signal? Once you can answer these questions, choosing the right learning approach becomes much easier. Now that we understand the different ways machines can learn, we need to step back and look at the entire machine learning engineering process. What happens when a real company gives you an ML problem? Where does the project start? How do you collect and prepare the data? How do you train and evaluate the model? And what happens after the model is deployed? That's what we will cover in the next episode, the complete machine learning project lifecycle. I'll see you there. Thank you for watching.